Hello, everyone. Welcome. I am delighted to be introducing the next keynote. The last keynote of OHBM 2024, last but definitely not least, and I'm really excited to have Professor Lucia Melloni to present that talk. I am Marta Garrido from the University of Melbourne, and I will be co-chairing with Sheila Kalehos from Atlanta. I'd like to also acknowledge that Lucia Melloni has her husband here in the audience and her son, Casper and Anton. Very warm welcome, and it's so great that you can be here. So Lucia Melloni leads the Neural Circuits, Consciousness and Cognition Research Group at the Max Planck Institute for Empirical Aesthetics in Frankfurt. She also holds a position as research professor in the Department of Neurology at NYU Grossman School of Medicine. Melloni's research addresses questions like why and how we perceive the world in the ways that we do, the potential for modifying these experiences through learning and the intersection of consciousness with cognitive processes such as attention, expectations, learning, and memory. She champions collaborative and open science, which are central to her research philosophy. With collaborators, she spearheads an adversarial collaboration, bringing together for the first time scientists from complementary disciplines with a common framework and a goal to arbitrate between established theories on consciousness. By combining multiple imaging and electrophysiology approaches in a rigorous large-scale project spanning multiple laboratories across the globe, it provides an example of a powerful and well-orchestrated interdisciplinary project that aims to unravel the neural basis of consciousness and what makes us ultimately humans. Leading an adversarial collaboration is incredibly brave. It is a mammoth effort and very challenging, as I'm sure Lucia will tell us about. And I believe it is absolutely the way forward to advancing the field. So thank you very much, Lucia, for leading us on this very brave journey of discovery. The title of her talk is Advancing Science and Theory Development Through Open Science Adversarial Collaboration. Please join me in giving Lucia a very warm welcome.
Welcome, everyone. Can you hear me well, or do you hear some echo? It's fine, great. So first of all, thank you, Marta and Sheila, and the whole, organizing committee for inviting me to, to give a talk today, and for also allowing me to talk to you about consciousness, which used to be one of those forbidden words. And it was really interesting to see that the first keynote was about subjective experience, and the last keynote is also going to be about subjective experience. So thank you, for allowing us to talk about this really weird word. The story today is going to be about, it's a tale of two, or a story of two tales. On the one hand, I will talk about the puzzle of consciousness, which, by all means was supposed to be one of the hardest ones, right? But it's also going to be about the puzzle of bringing people together who disagree to amicably resolve disagreements. And those are the scientists who hold different views. And I used to think that cracking consciousness was really hard until I started this adversarial collaboration. And this is just a reminder for all of us that it's important for the scientific community that we come together and we find ways to really discover the truth together. And we need to get it right, not to be right. So that's the start. So what is the problem? And the first puzzle is, all of you yesterday went to this fantastic party. Probably you disappeared in dreamless sleep, and you wake up this morning with this TV on again, right? So, we disappear, we appear, and this happens to millions of people every day that lose consciousness and then regain consciousness. But that magic sometimes does not happen to some people. And I had almost 24 years ago by today, the really difficult experience of finding a relative of mine who was declared brain dead. And when you are confronted with that, not as a scientist, but as a person, as a private person, it's really hard because you have to say goodbye to somebody who can actually breathe apparently, who can also even have reflexes and move, like his or her hands. And you are left there wondering, like, is somebody there? And that's something that, even as a scientist, you cannot shake off that thought. That night, I am a lucid dreamer, so I started like wrestling in my thoughts, with this image, right? And I came to the following realization, which was really, I would say, somewhat foundational in my career. How could you, as an audience, distinguish who is there? This person who is moving and is declared brain dead, or me, who is there completely paralyzed, but in my thoughts and in my mind, I'm completely there. And that's the puzzle of consciousness. We can be there without necessarily movement. So what is it? Or what is the definition I'm going to use today when we talk about consciousness? I will define it as something very simple, which is experience. And that means that sometimes this experience can be accompanied by movement and by outer behavior, but it doesn't have to be the case, as I told you before with the dreamless, with the lucid dreaming. It's also private. We all have it. Like, you have it now. Like, even if I ask you, like, are you there, are you not? Of course you will know, like what you're experiencing right now, right? Moreover, you won't even need a measurement. You know it. You know that you have it, right? So it's experience, it's direct, and it's subjective for yourself. Yet, as a scientist, it's really hard to understand this problem. Why? Because while I'm certain about my own experience, I cannot be certain about anyone's experience, not even my kid who is sitting here in the audience, right? I have to infer that whatever he is experiencing is similar to what I am experiencing, right? And this is so-called like the subjectivity gap. So how do we go from the first-person perspective to the third-person perspective as a scientist who tries to understand this puzzle? How do we do that? We always have to rely on report, some kind of report. Either we ask people, we ask the brain, we ask eye movements to tell us, like what's going on, and so on. And over the years, we actually have become better and better at actually having psychological tricks to infer whether or not somebody is experiencing something or not. We can, for instance, in this case here, let me just use this. You see the mouse, yeah, okay. As in this case here, you can, for instance, present two different Gabor patches, like two subjects, and then if you have them in binocular rivalry, they can perceive either one or the other. And then the subjects can either tell us like it's perceiving one or the other, or their eye movements can also tell us, like what they're experiencing. For many years, and after the whole, behaviorism, it was really, really hard to convince scientists that it was possible to investigate this, right? Because there was not a really good measure that we could rely on. But in the 90s, Christoph Koch and Francis Crick, they thought, okay, let's just try to have, or leave aside all of the philosophical debates, and let's try to concentrate on a much simpler problem, which is to define the neural correlates. And how did they define it? They search for the minimal neural mechanisms jointly sufficient for any conscious experience, perception, the NCC, and for every conscious percept, there will be an NCC. Inducing the NCC will induce the perception, inactivating the NCC will eliminate it. And the idea here was very simple. I will present you with the stimuli, I will take some measurement of inactivity, and I will see actually what changes, right? And as you can see here, if you look at, how many studies were done on, the neural correlates of consciousness in 1990, it was about 16. But today, you can see this really, really stark, the field has really flourished. We have, just in 2024, 553 studies published on that. So this, by all margins, it was the start of a really fruitful scientific program. To the point that nowadays, we have theories. We have collected, almost 30 years of data, and people have developed multiple theories for consciousness, right? The problem is twofold. On the one hand, that those theories do not explain consciousness in the same way, and that is tantalizing or difficult to understand. I mean, one would imagine that there is one truth out there, not many. But the second is that the list of theories goes on and on and on. And that is also problematic, right? Why is that? Many years ago, with Liad Mudrik, Michael Pitts, and Itai Yaron, we look at the literature in the consciousness field. We survey, in this case, 478 experiments, and we try to understand, like, how come that, one would have imagined, or at least, like, that was my thought at the time, would it not, if we have become better understanding consciousness, should it not be the case that we are somewhat converging on certain views? So some views are, like, becoming more progressive, some views are actually dying out, right? That's what I would have expected. That the data shows something very different. What the data shows is that if you take the 4 major theories of consciousness, in this case, Global Neuronal Workspace theory, recurrent processing, integrated information theory, and higher order theories, the amount of data that supports them is really high, right? But the amount of data that challenge them is really small. So you would say, okay, come on. I mean, how come I can have like 4 different views and all of them have exactly the same amount of support? Then you would say, well, it could be that this is just a snapshot of the last 30 years. What happens if you then do it like over time? Perhaps over time, some theories are gaining more support. The evolution of ideas, they are becoming stronger, and some more are dying out, right? Again, it would have been an interesting thought, except that that's not what we see. If you see actually over the years from 2000 to 2020, every single theory seems to be becoming stronger, right, in terms of the amount of data that supports them. Now, if you divide this by supporting versus challenging, what you see is the support for them is significantly larger than the challenge for any one of them, right? So these are very, very clear signs of confirmation bias and very limited crosstalk, right? Moreover, which is even more problematic, if you then ask, okay, where in the brain the neural cortex of consciousness are? If you put all of the data, it's everywhere. But if you divide them by theory, you find a huge theory bias. So the NCC for consciousness for one theory looked one way. So imagine that in this case, recurrent processing is only in the occipital cortex. For higher order theories, it involves the prefrontal cortex. Once again, you would have imagined that it doesn't matter which theory you pick or which data you pick. You should have ended up with the same NCC, right? But here, clearly, you see that this is not the case. That people look and find what they really are looking for, right? Now, this is an old problem. It's actually not that. I thought that we had solved it somewhat, but Walter Mitchell, in his presidential APA, urban legends things, he talked about the so-called the toothbrush problem, which is very simple. It says psychologists treat other people's theories like toothbrushes. No self-respecting person wants to use anyone else's. So if that is the case, how are we going to find the truth? At least that was my wondering. Right? Max Planck, so the problem then becomes, how are we going to really find what the mechanisms for consciousness are, or for that matter, attention, working memory, whatever, right? I think the toothbrush problem is not just on consciousness, on the conscious research, it's everywhere. So Max Planck had a proverb. He thought that you would not convince people, of your ideas. You would triumph because your opponents would die. Fine. I mean, it's just going to take a while until we find things out. So in thinking that, even though I am a Max Planck person, I prefer to think that there is alternatives, we thought, could we think of a better way or a different way? And luckily, Danny Kahneman, also in 2000s, he had proposed that a way to resolve what he called angry science and disagreements was to rely on adversarial collaboration. His idea here was very simple. You collaborate with the person that you disagree with. You come up with an experiment that you think that is decisive. You prepare the predictions before, a priori, before you collect the data. You agree to publish the paper whether the results are positive, negative, or a draw. And you also agree to change your mind in the face of the results, right? That's the protocol. And this is what Danny says.
You have to be willing not to win. That is, you have to be willing to accept a draw. And to see that in the interest of science and, you know, and civility and other things, a draw is better than a win. I happen to find a few people who are willing to do that. By the way, it is not easy because, you know, people who think poorly of your work and of your ideas get on your nerves, and so you have to overcome that.
He has managed to embark in many adversarial collaborations, so he knows very intimately what it means, you know, to actually sit down at a table with somebody that you disagree with. And as I said, the protocol of these adversarial collaborations look very different, and even the papers look very different. So, you know, you now publish a paper with even a discussion of 3 voices. The arbiter, in this case, you know, say me, and the 2 different opponents, right? And why is that important is because you want to unravel the whole truth behind the process. You want to tell the audience what you thought before and what you think after the results are published. All right, and with that in mind, this is the birth of what I want to tell you today, which is COGITATE. This is a large-scale consortium of 11 institutions and over 50 scientists who, you know, in 2018 came together to test 2 theories of consciousness. One is Global Neuronal Workspace theory by Stanislas Dehaene, and the other one is integrated information theory by Giulio Tononi. And these 2 theories cannot be more different, not only in terms of, you know, like which areas of the brain they think that are relevant for consciousness, but also their starting point. In a nutshell, for Global Neuronal Workspace theory, what matters is that, you know, the information needs to be transferred or broadcasted to a frontoparietal network for the messages that are unconscious to become conscious and distributed in a network. 2 things are important for that theory. One is it has to activate the frontoparietal network for this message to be broadcasted, and it has to be ignited. What that means is that only there's a late wave of activity that comes into frontal cortex, and then the message gets distributed. For integrated information theory, they say, no. Consciousness is not a message. It's a structure. It's a structure of integrated information that can be measured through a measure called phi. And in simple, or in a nutshell, what they propose is that information has to be integrated, differentiated. And for that, not only the activity, but also the connectivity matters in terms of, you know, whether or not someone is conscious. Because of the architecture of the brain, they also assume that it's the posterior areas, in this case, that make a difference for consciousness because they have more lateral connectivity as opposed to more random connectivity as the prefrontal cortex. So in simple, for IIT, the posterior areas are necessary for consciousness, and for GNW, the prefrontal cortex is sufficient, right, to be for consciousness. So with these 2 theories, we then came together with the 2 adversaries to define experiments. And then we also look at 3 different measurements in this case: fMRI, imaging, and integral recordings. Why? Because we wanted to really get an answer that was substantial, right? Partly because when we were devising the collaboration, I thought, you know, you have to become like a detective. Like, what are people going to tell me afterwards? They're going to say, oh, no. You know, you didn't find it in EEG. You didn't find it in fMRI. So therefore, the results that you find are not sufficient, right? So we thought, okay, let's just take all of the measurements, you know, from human neuroscience these days, right? So then the answer become hopefully acceptable to both of the adversaries. On top of that, we also did highly powered studies. We collected, in this case, like over 500 subjects. We had to standardize the methods because we had fMRI, EEG, and intracranial recordings. And we also have an inbuilt replication. We had 2 labs, or 3, running the experiments in parallel. And we thought, whether we like it or not, unconscious bias is a thing. So let's have the adversaries giving us the predictions, the outcomes, and for us agreeing on the potential ways to falsify their theories. But let's have other teams, hopefully theory neutral, who run the experiments, right? So when did we start? As I told you, we started in March 2018. We met at the Allen Institute. It took us almost a year to come up with the experiments to test IIT and GNW. And we came up with 2 experiments, and they are complementary. The first one is addressing the question of what mechanisms underlie the rich aspect of conscious experience, irrespective of the task, and what is the mechanism for the maintenance of consciousness. And the second one asks the typical question of what are the mechanisms for seen versus unseen. Why we actually decided to have to experiment is because they address two different questions, and because we think that convergence evidence, you can think of a joint probability is much more difficult than a single probability. So if you're really going to go and try to test a theory, it has to pass all of the different tests for it to be truth, right? Or just one of them would be enough to falsify the theory, right? Then after we came up with the experiment, more importantly, we had to come up with a set of predictions from the theory. So in this case, you could see the key hypothesis, the test that we were going to run, which I will explain you later on. But more importantly, cases in which we would think either make the theory to pass or to fail. And this was a priori, right? Because, of course, if you run the experiment and then you have the predictions, then, of course, it's just not going to be it's not going to cut it, right? And we did this both, of course, for IIT and for GNW. Then, we now have what Danny did not have back in the day, which is pre-registration. So we pre-registered. We did a register report. This was reviewed by, external reviewers. It's also published in PLOS One as a registered protocol. And after that, importantly, because again, you think of, like a detective, right? So I asked Stan and Giulio to send me a letter before we started all this, saying the following. The experimental design as proposed is suitable for testing specific predictions of the global neural workspace theory, and I concur with figure 7 in the pre-registration showed the possible outcomes that would support or challenge the predictions of this theory. Why was that important? You will see later on. Again, I think this is really interesting when we think about, like, okay, this is social engineering, so we need to understand with the kind of people that we're dealing with, right? So we started the project started right when the pandemic kicked in, so it was really hard, but we managed to collect fMRI data, EEG data, and ECOG data. In this case, we collected 120 subjects for fMRI, 102 subjects for EEG, and 34 subjects for ECOG. What is important is that, as I told you before, we had a replication phase. So we used 1/3 of the data for optimization of the analysis, and then 2/3 of the data for the replication. And what I'm going to show you next is only the replication phase. In the paper, with a supplementary of 100 pages, you can see everything. But here in this short talk, I'm just going to give you the last part. So of course, we pre-registered the optimization analysis. We ran the replication. We have the paper out since a year. But this is just half the way. Why? Because we have a second experiment, which we are analyzing, so there is more to come. Right? But for now, I just want to concentrate on the first experiment. In the first one, which we call the Mona Lisa, is trying to ask a very simple question, which is, if you see the Mona Lisa, you immediately know there's a woman and not a man. You immediately know that it's looking in a particular direction, right? You also continue seeing her if you look at her for 1 minute. So, and that cannot be magic. There must be something in your brain that explains every feature of that experience, right? And as a scientist, what we did in this case was to present just one stimulus on the screen. We're not that, good as Da Vinci. So we presented in this case faces that are like these face-generated faces, objects, letters, and false fonts. And that would actually capture the category. For each of those, we had 3 different orientations. We had 20 different identities for each of them. And we manipulated the duration of all of those stimuli. They can either be presented for 500 milliseconds, a second, or a second and a half. And we're looking for what is the activity in the brain that explains all of these dimensions. And more importantly, we also needed to discard the task relevance. Why? Because in the field of consciousness, there is a lot of discussions about whether or not activity in prefrontal cortex can be explained by just subjects doing a task. So we had some of the stimuli that were task relevant and some of the stimuli that were task irrelevant. How did we do that? We presented one stimulus on the screen, and subjects had to identify 2 of them out of the many, right? And so every other stimuli was not task relevant. We had 3 predictions, and as I told you before, this is important because it's not that each prediction is important, it's the combination of them that makes the test more difficult to pass. We had three. The one was about the content of consciousness, and here the question that we ask is, where in the brain can we find information about the contents of consciousness? The second one, with respect to the maintenance, what are the neural mechanisms allowing perceptions to endure in time? The third one is, which ones are the areas that explain synchronization patterns in these theories? And I will explain you very briefly what are the different hypotheses that we have here. With respect to the first one, the idea is that, at least for GNW, it's important that in the prefrontal cortex, every conscious information should be there. So this means that information about category, identity, orientation, etc., should be present. And where should be present? In the prefrontal cortex. In which areas? The ones that you see in green here, right? For IIT, they say, no, only the posterior areas are sufficient to be conscious, and therefore we will look for contents of consciousness only in the back of the brain, right, in these areas that are in blue. I'm going to show you just a brief glimpse of all of the data because it's a lot to cover, but in this case, what you're seeing is, this is the work of Aya Khalaf at Yale, and two things to note. So first is here you can see, here you can see the arrow eyes that each of the theory leads identify as the ones where we had to look for the correlates of consciousness. So in this case, the green ones represent a Global Neuronal Workspace theory, and the blue ones represent IIT. Right? And what you're seeing here is the coding of category, in this case, faces versus objects. When you do cross-classification, so you take faces versus objects in the task irrelevant, and you try to cross-classify to the task irrelevant. And as you can see, there is very good classification in occipital cortex, as well as there is very good classification in prefrontal cortex, right? You can see here. Now, importantly, if you then do the classification the other way around, now you start from task relevant to task irrelevant, you recover more or less the same areas. So what this means is that the task itself can be discarded. Now, based on that, you would say, well, both theories pass the first hypothesis. We then tested that also with integral recordings. Why? Because for GNW, they make a claim that it's only late activity that should correspond to consciousness. So we had to look for temporally resolved signals, which we did in this case through intracranial recordings. This is the work of Simon Henry and NYU. And again, what you can see here is cross-classification between task irrelevant to task relevant. And again, we recovered the very same prefrontal areas and the very same posterior areas, both for task irrelevant to irrelevant, as well as for task relevant to irrelevant. So once again, you would say a draw. Both of theories pass. Now, importantly, we had one condition, which is orientation. Orientation was always task irrelevant. And as you can see here with fMRI, in the results of Aya, we find very nice classification in occipital areas, but nothing to be seen in prefrontal areas. Then you would say, well, you didn't have time-resolved signals. We did. In this case, we had integral recordings, and there, once again, we could not recover any decoding from prefrontal areas. So based on that, we will say GNW's predictions are falsified, and that represents a challenge for the theory. One caveat is that we also had EEG. The reason why the prediction here is in yellow is because with EEG, we did find decoding in prefrontal cortex, but we could not convince ourselves there was not leakage from posterior areas. So therefore, we did not mark it as a full challenge, but a significant one nonetheless. Okay, the second prediction is, what are the mechanisms allowing for the percept to endure on time? And here the manipulation of, the duration of the stimulus become relevant. Why? Because for GNW, what matters is that the stimulus have to enter into consciousness. And for that, there is an activation and an ignition in prefrontal areas. That activation should not or shall not be maintained throughout the percept, but it only has to be reactivated at the end of the percept. Therefore, you would actually find, or you would look for patterns such as this one, whereby for a 500 millisecond stimulus, you would have an onset at the beginning, an onset at the end, and then the offset would be protracted depending on the length of the stimulus, right? And this is the pattern that we should find in prefrontal areas. Now, what about IIT? For IIT, because they consider that the structure of your experience should be somewhat mimic in the same structure in your brain, they consider that the activity, the content, and the connectivity should be maintained throughout your experience, right? So therefore, in this case, we should have activity that lasts for as long as the stimulus is present. In this case, either 500 milliseconds, a second, or a second and a half. So the predictions would be for GNW, onset and offset responses, and for IIT, sustained content specific. Furthermore, we tested this with RSA because it's not only important to find that there is activity there, but the contents should also be there and should be there in a particular way. So for GNW, they should be present at the very beginning and then be reactivated at the end of the experience, whereas in the case of IIT, they should be maintained, and those patterns of activities as measured through RSA should be present for as long as the stimulus in the subject's mind. What did we find? This is the work of Alex Lepeuvre in my lab in Frankfurt. And I'm going to show you here only the ECOG results because those are the ones that are most relevant due to the time result. And what you can see here is, like first for the predictions of IIT. You are looking at, in blue up there, is the areas in which IIT had made the prediction. We had 500 electrodes in occipital cortex, of which only 12 showed these sustained responses that would scale with the length of the stimulus, right? So by all means, it's a pattern that is present there, yes, but it's not a prevalent pattern if you think about 500 electrodes that we had, right? We had 12 that were non-selective and 8 that were phase selective. And as you can see here, this is when the stimulus lasts 500 milliseconds, a second, or a second and a half. So based on that, the prediction is fulfilled. Now, what about information content? When we looked for representational similarity with respect to category, we do observe very nice representational similarity that scales with the length of the stimulus that was presented. So in this case, a second and a half. And you can see here by a multidimensional scaling how the different categories are separated. The same holds true for identity, and this is relevant because identity is here where they had to be irrespective of the orientation, left, right, and front, right? So we also find information for identity. So based on that, we would say the predictions of IIT are fulfilled. What about the predictions of GNW? We had, again, 500 electrodes in prefrontal cortex. You can see here that in around 100 of those, we found very nice responses that were an ignition in prefrontal cortex in this case, but none of them showed the offset response that was predicted by GNW. There was one exception. There was this single electrode here, right, that you can find an onset response and an offset that scales with the duration of the stimulus. Problem was that it was actually earlier than what the theory had anticipated. But it's important for us because it tells us that had those patterns been there, we would have been able to capture them. What happens with respect to representational similarity? We do find very nice, in this case, decoding of category at the beginning of the stimulus, but nothing at the offset of the stimulus. What happens with respect to identity? We actually do not find any information with respect to identity whatsoever. So based on that, we would say the prediction is falsified. What about the last one? The last one reflects which ones are the areas that should be synchronized. And you can think of, in the case of GNW, the message needs to pass from high-level visual areas to prefrontal cortex for them to become conscious, right? And therefore, we should, and that particular prediction should lead to synchronization patterns between, in this case, for instance, phase-selective areas and the prefrontal cortex. In the case of IIT, they also think that this cause-effect structure should be reflected in patterns of synchronization that link, for instance, like low-level properties of the stimuli, such as contours in B1, as well as high-level categories in FFA. And more importantly, and this is the key for IIT, that patterns of synchronization should be sustained. Contrary to GNW, that only requires it to be as an ignition, in the case of IIT, it has to be sustained because that's actually what leads to the percept in the mind and the cause-effect structure. Right? All right, so we tested this through two different ways. So Aya did PPI analysis with fMRI. She put her seeds in FFA, and then she can recover areas very nicely, both in B1 and B2, which are compatible with IIT, as well as in prefrontal cortex and parietal cortex, which are compatible with GNW. Now, the problem with PPI is it's not a time resolve measure, and for this, it's really important to timely resolve, because the predictions are, as I told you before, for IIT in particular, is relevant that this pattern of synchronization must be sustained. If it's not sustained, then it's not compatible with the theory. So to get at that, Simon looked at the intracranial recordings, and again, good for us, we could actually recover synchronization between phase-selective electrodes and prefrontal cortex, which are compatible with GNW. We could also recover synchronization between FFA and B1 and B2, except for the fact that it was not sustained. So therefore, based on that, we would say the predictions of GNW are fulfilled and the predictions of IIT are not. So where does this lead us? To a lot of bloody red, I would say. So when people ask me who won, I would say that's the wrong question. Why? Because what we set out was to falsify theories. And having one red was enough for the theory to be falsified. So I would invite us to think about, I see a lot of red there. But my claim is that this is just one piece of the puzzle. Why is it one piece of the puzzle? Because we are here ideally to do even more. We have a second experiment that we are analyzing at the moment. There's a second adversarial collaboration that is testing the same experiments I told you now in animals, in this case in mice and in monkeys, with causal manipulations and single units. So my hope is that we will see more about this and we will learn more. But at the same time, I think that one of the things that we discover is that it's really hard to do science this way because you need to find ways in which you integrate evidence across multiple tests. And that is by no means an easy problem, as I found out. And my hope is that, as we do this more and more and more, we will also change the way in which we do science, and we will become more comfortable with just, being brave and testing our theories and our predictions, and consider that what we are here for is to find the truth, right? Moreover. We did not just run this because it was really costly, to test these two theories. The real plan was also to give this data to the entire community. And so now we are preparing the data for all of you to look at, fMRI, imaging, and ECOG on this experiment and the next one to come. We have also run with Ole Jensen, Juan Luo, Oscar, and Ling, challenge at Biomag for the connectivity. And our hope is that, together, we will not only use the data that we had to test these theories, but any other theory you can come up with, right? Now, this was the first project out of 4, in this case, who are testing different theories of consciousness. So my hope is that in the next 20 years, this graph that I show you that has a continuous growth will show some dips, and it will demonstrate that not all of these ideas were equally right. Now, when we started the adversarial collaboration, Danny had created or had thought of this as a way for people to change their mind. And I think that it was in 2021, I don't remember, Sylvain, but 2022, we invited him for a talk in our consortium. And he said to me, you know what? Actually, I never changed my mind. And even more so, the reason why I never changed my mind is because of the so-called 15 IQ point benefit in simple hindsight bias, which means that you always explain things away after you have seen the results. Now, I invite you to read our paper. There's a discussion of 3 voices, and you will tell me whether or not the people in my consortium changed their mind or not. With that, I would like to just, have some, home messages for all of us, or perhaps areas to consider. Even though in 2008, Walter Mitchell talked about the toothbrush problem, I think it's interesting to see that it has been there ever since, and we have not really changed it. So I hope that adversarial collaborations will be a mechanism to resolve those disagreements, but it will require a different set of scientists, a scientist that truly embrace, that part of the science is to just be challenged, but also a set of different incentives for us, where we allow people to be wrong, right? And we don't punish them, right? And part of the problems that we have these days is that we are only rewarded for being right, but we are not rewarded for being courageous and test our theories or our hypotheses to the fullest. So my hope is that one day we will really all aim to get things right and not to be right, and that as a community we will embrace collaborative challenges and intellectual humility. And with that, I want to thank the people who did the work. These are the amazing students who bravely decided to embark into this adversarial collaboration, and not to test their own theories, but change of a different career, or think of a different career where they look into somebody else's, like a hypothesis, and they embrace different toothbrushes, And of course, Templeton for having supported this adversarial collaboration. And as a last point, I would like to really acknowledge Danny. Why? Because when things got really, really hard in the adversarial collaboration, the one person who picked myself up was him, And I really want to, this is just also for all of the youngsters in the audience, like doing science is really hard, but if you find one mentor, who picked you up in those moments when things get hard, it gets much, much easier. So, And with that, I just want to thank everyone and the OHBM, and thank you, of course, for your attention.
Thank you so much for that fascinating talk about an experiment in doing science. We've got some questions in the chat. I'm going to combine the first two. They are, is the brain necessary to experience consciousness? And how would you determine whether an AI is potentially conscious?
Two difficult questions. So we think that the brain is relevant, just because of, studies with lesions and patients, whereby if you, have lesions in your brain, then you lose consciousness. That's one of the reasons why we think that the brain is relevant. Is it the only thing? I don't know. I am on the fence. I think that one of the things that we have not looked enough is at the connection between the brain and the body, especially for lived experience. So I would like to hope, or would like to see more research trying to link the brain mechanisms with also the body. As for AI and consciousness, I think that's the reason why I think that doing this research is really relevant, because we don't have answers at this point, not just for AI. We don't have answers for patients, for infants, for animals, and also for machines, right? People have, relied on these theories as a way to make inferences, right? But if these theories are wrong, then also our inferences are going to be wrong. So my hope, again, is that, we really try to test these hypotheses in such a way that we then gain more confidence in the hypothesis, and therefore can use these theories to make, hopefully, inferences for animals, babies, machines, and so on.
Fantastic. So there's a second question that's very popular, a little more pragmatic, which is, scientists can be willing to not win, but the funding agencies and the hiring committees reward people who win. Is that a problem?
That is absolutely a problem, and that's what I was trying to hint at with we need a different set of incentives. Now, one of the things I always tell my students is we are the system. Because every time, like I hear about this, it's like the system. It's like as if I'm not part of it, right? So my hope is that we will change the system. We are hiring committees. We can talk to funding agencies. In this case, Templeton was really brave in funding adversarial collaboration as a mechanism, and therefore, in this case, like rewarding us for testing our hypothesis. After Templeton did this, we sat down with NSF, with program officers from NSF and NIH, to look for funding mechanisms also within NSF and NIH for this kind of research. Will we succeed? I don't know, but my hope is that once again we will, as a collective, really make a priority to understand that we are here, for the truth, and that even though there is a tension between the scientist and the science, we will somewhat change that, and embracing intellectual humility and embracing that we need to challenge ourselves is a part of the science. And if we cannot do that, then how are we going to convince the general public? I think that I'm actually less concerned with the kind committees and with the funding agencies as with the general public. We want to tell them that what we find out is the truth. But if we can't really test that, then we're not living up to our promises.
Very inspiring. Let's all keep pushing to change the system. That's the end of this session, so thank you all very much for coming, and enjoy the rest of the meeting.
You're also speaking, I guess. Just wanted to get a feeling of like, hello.